In chemistry, we'll be doing many different calculations in our activities and labs. So in this lesson, I'm going to show you how to round the answers to calculations to the appropriate numbers of significant digits. The significant digit rule for addition and subtraction problems is this. The answer to the problem will have the same number of significant digits past the decimal as the measurement with the fewest digits after the decimal. Here's an example of where that calculation rule might apply. Let's say you have three different objects. I'll call them A, B, and C, and you have three different students weighing these individual objects. So one student takes this object A and he puts it on a balance, and it's a pretty nice balance, like a lab balance that we'd have in our classroom. And this balance costs about $278, and it will record the mass of A to two places past the decimal. So he records the mass of A to be 32.12 grams. Another student takes object B and weighs it on a balance that's pretty cheap. The balance is only $47. It's a kitchen balance. It only records masses to one place past the decimal. So this student records the mass of object B and finds it to be 6.0 grams. Finally, the third student uses a really nice analytical balance that's quite expensive. As you can see here, it's almost $1,900 for the balance. And the reason it's so expensive is because it takes really precise measurements. So this balance can actually record masses to four places past the decimal. And this student records the mass of object C to be 0.0211 grams. And your job is to determine with the correct precision what the sum of the masses of all of these three objects are. So you decide to add up all these mass values and you end up getting 38.1411 grams. The problem is that really the precision with which you can mark your final answer can only be as good as your worst balance. So to account for that, what you do is you realize the value that has the fewest places past the decimal is the 6.0 right there. So you're going to have to round your answer to one place past the decimal. So you would actually record the sum of these three objects to be 38.1 grams. Now you might say, well, what about this 4, 1, and 1? Doesn't that matter? It doesn't really mean anything because really if we were to take this object right here that weighed 6.0 grams on this balance B and we were to put it on this very, very expensive balance, we might get a mass of 6.275 grams because it'll be measuring more precisely. It'll actually give us the true value for these digits past the decimal. So basically, we have no idea what these values are using this cheaper balance, so it doesn't make sense to just assume that they're zeros. And so we don't make that assumption at all. Our final answer can only be as precise as our least precise measurement. The subtraction rule is the same as that of the addition rule. So to do this problem correctly, we take 3.0, subtract it from 7.251 to get 4.251. Find the value that has the fewest places past the decimal, that's the 3.0, and round your answer so that it has the same number of digits past the decimal as the 3.0. So your final answer is going to be rounded to 4.3 centimeters. I had to round the 2 up to a 3 because there's a 5 next to it, so that rounds it up. The rule for multiplication and division is different from that of addition and subtraction. Here's the rule for multiplication and division. The number of significant digits in the answer is the same as that of the measurement with the fewest total significant figures. Here's an example. If we were to take 8.032 and divide it by 0.0591, we would end up with this answer. 135.9052453. So to understand how to round off this answer, what you want to do is count the total number of significant digits in each one of the numbers in your problem. 8.032 has a total of 4 significant digits. And 0.0591 has a total of only 3 significant digits. Remember, these zeros here are not significant because they're just decimal placeholders. So, of the 2 values in your problem, this one right here has the fewest total significant digits. It's got 3. You need to round your final answer to 3 significant digits. This will make our final answer 136, the 9 rounding the 5 up to a 6. Here's just another example. If we take 9.33 and multiply it by 0.0021, we will get this answer, 0.019593. So to solve this, we want to figure out how many significant digits are in each of the values in our problem. 9.33 has 3 significant digits. This next number only has 2 significant digits, so our answer can only have 2 significant digits. So what we want to do is find the first 2 significant digits in our final product, and that would be the 1 and the 9. So we get to keep those. The 5 next to the 9 will round the 9 up to a 10, which in turn will round that 1 up to a 2. So our final answer will be 0.020, or you can write it in scientific notation if you want to, as 2.0 times 10 to the negative 2. One last example, this is a division problem. So our first value here, 101.00, every single one of those zeros is significant, so that would be 5 total significant digits. Divided by 43.9006, every single one of those numbers is significant, so that gives us 6 significant digits. So our final answer must be rounded to 5 significant digits. So I'm going to underline the first 5 significant digits. 2.3006. We're going to keep those. There's a 5 next to the 6, so the 6 will get rounded up to a 7. And our final answer will be 2.3007. This is just a quick memory tip if it helps you out. The plus minus rule, or the one for addition and subtraction, says the plus minus rule is look at places past the decimal, and then for multiplication and division rule, just match significant digits. Sometimes in the lab, we'll take numbers and we'll do lots of calculations with them, several multiplication and division steps, one right after the other. And the important thing to understand is when you're doing this, you don't actually round until you get to your final answer. However, here's a scenario we're going to see a lot. It's percent error, and it's unique because it involves a subtraction and then a division. So I'm going to go through and show you how to deal with significant digits for this problem. For this percent error problem, the question says a temperature is measured to be 32.5 degrees Celsius, and the actual temperature is 30 degrees Celsius. What's the percent error? Well, to solve this, what we do is we take the difference between the actual temperature and the measured temperature. So we have to subtract these two numbers. So you should subtract them and round to the appropriate number of significant digits at that point for subtraction. So that's going to give you 2.5 degrees Celsius, because that's actually a measured value for the difference. And then you're going to take that value and divide by the actual temperature, 30 degrees Celsius. Now you can almost think of this as a separate problem, and you're going to take the 2.5, divide it by the 30, and multiply it by 100, and use the division rule for significant digits here. When you do the math for this, you're going to get 8.333 repeating, but you want to round your answer to only 2 significant digits, so you'll get 8.3%. The reason being is that this 2.5 only has 2 significant digits, the 30 has 3 significant digits, and the 100 actually has an infinite number of significant digits because it's not a measured value, it's an absolute value that gives us percentage. So you want to round your final answer to two significant digits, giving you 8.3%. With a little bit of practice, these rules get easier and easier to follow. So hopefully this little tutorial will help you to get started.